Okay, gentlemen, we will talk about a ship coming to the surface now. What is the main difference between a submerged body and a body floating in the surface? The main difference is now the body is moving in two media instead of one medium, and between the media there is a surface which is free. We call it free surface. That surface, the geometry of that surface will depend on interaction between the two media and basically the pressure. Do you understand? Now, suppose for example, you see a water wave on the sea surface. Can you tell me what is the pressure on the top of the wave surface? Top of the surface. Top surface. Suppose I have got a wave surface like this. What is the pressure here, here and here? Is it constant? No? Then you are in big trouble. It has to be constant and equal to atmospheric pressure.
Pressure must be less there, then only it is going up.
No, pressure here and here are different. They are adjusting themselves in such a manner that the pressure on the surface is constant. It has to be constant. That is the atmospheric pressure.
It's the wind that keeps them moving up and down. Otherwise, under normal condition, there will be a total straight line.
Yes, if it is straight line, there is no wind. Pressure is same. Pressure is atmospheric.
So that is physically we can make out that sound, but this one is changing and has to have some.
On the free surface, it must be constant pressure. This is simply one of the conditions imposed on any flow, that the pressure on the free surface, otherwise it will not remain free, it is constrained, it is a free surface. Therefore, the pressure at any point is equal to atmospheric pressure on the free surface. It will vary drastically as you go down, it will vary as you go up. The atmospheric pressure will change because of the velocity of the air. Here it will change because how can you have high pressure, a pressure here and without any variation. So, that will change, but the surface itself, the pressure will be constant. Okay. Now, you see you have got let us go back to the this page when we discussed about distribution of pressure due to potential flow. Now, there is a high pressure here and a high pressure here, right. Now, you have brought the body up to the surface, still the flow around it will generate high pressure here and high pressure here. What will this mean? How will the free surface behave? As soon as you have a high pressure point, it will generate a wave. You understand? As soon as a high pressure point, it will push the water up till such height that the atmospheric pressure becomes constant. It becomes atmospheric pressure. So, there will be a wave generated due to generation of high pressure due to potential flow or non-viscous flow. Do you understand that?
Non-viscous.
Is non-viscous. We consider non-viscous. Viscosity is there, but apart from that, in the forward end, we have seen that there is hardly any effect of viscosity. So, primary forward wave generated by the ship will be due to generation of high pressure at the forward end. Clear? So, what will happen is a wave will generate at forward end. Similarly, a wave will be generated at the after end. There may be small waves generated elsewhere in the ship. We will see it as we go, as we discuss wave making resistance in more detail. There may be further waves generated in along the length of the ship because of generation of high pressure. Wherever there is a high pressure point along the length of the ship, a wave will be generated. Now, how is this wave generated? There are two sets of waves. Again, we will see it in further detail later on, but primarily there will be a set of transverse waves which are transverse to the direction of the ship, going away like that, and okay, ship is moving like this, that is water is moving like this. This is ship, that means water is moving in the opposite direction.
This is the plan B.
It is a plan. There will be a set of waves going away like this is called divergent waves. Okay, that is a set of waves which will go far away in the transverse direction, they will diverge, and a set of transverse waves, waves the crest of which is in the transverse direction to the longitudinal axis of the ship. You have seen this, you all must have seen this, you must have seen photographs where they show the divergent waves of a ship. Yes, and if you have observed a flow around a ship, you would find that near the ship body, see this is the body, so you won't see anything here, isn't it? You will see crests near the ship hull which is going in the transverse direction. Have you seen? So, you will have two wave systems generated around the body. Now, these waves, as we know, waves are carriers of energy. So, to sustain this wave making in a continuous manner from the ship will have to spend energy. That is called wave making resistance, which was not there when the body was submerged in water. This was not there, no waves were created. Do you understand? Just imagine for a moment that there is no viscosity. Okay? Just imagine for a moment that the fluid is without any viscosity, like the non-viscous fluid we saw in this case. When the body was immersed, we found that the opposing force is equal to the supporting force, and we had the D'Alembert's paradox. Now, we have brought the same body up, same non-viscous fluid, but now the waves are being generated. Waves are being generated means what? Energy is being taken away. Now, you cannot say that the resistance is 0. Do you understand? Physically, you see the waves are being generated. Waves are, you might have learnt that waves are basically a gravity phenomenon, and it is not affected by friction, by viscosity. Yes, it is not affected by viscosity. So, therefore, all ocean waves, that is true for all ocean waves. In fact, that is true for all waves, basically a pressure phenomenon. Here also you have a pressure phenomenon. Unlike the body when it was submerged, you had the D'Alembert's paradox that there was no, assuming a non-viscous fluid, there was no resistance to forward motion. As the body comes up to the surface, there is resistance to forward motion due to generation of waves. This is also due to a pressure phenomenon, but the effects are different. You understood? Let us see what happens to viscosity. Is viscosity there? Of course, it is there. You have the frictional resistance, as we discussed, the boundary layer develops and it becomes wider as you go towards the back of the ship. Same thin boundary layer coming right up to the surface, free surface. So, there is a small thin boundary layer right on the free surface itself along with the wave. You have the viscous pressure resistance. How does it manifest here? Here the stern wave is damped, though the stern wave effect will be same. It will try to reduce the, it will try to support the motion. We have seen that. That depends on Now, it depends on where the stern wave is generated. For example, if the stern wave is due to some odd shaping of your body underwater, if the stern wave is generated aft of the stern, then you may not get the support. Can you understand this? No. Okay.
Wave making is strictly a surface phenomenon.
Wave making is strictly a surface phenomenon. That is correct. Wave making is strictly a surface phenomenon. As you go down, there is no wave making.
Only turmoil or eddy drag, you said that is underwater.
That will also be there on surface ships. Yeah. Let us take two cases. What I am saying. Suppose you got a wave which has a stern leg. I am not talking of the aft. Let us say this stern. The pressure is high here. So, when the body is here, if I draw the body here, the pressure is high here. Therefore, there is a large component supporting the motion. This component. Is that clear? Let us take second case. Somehow the crest is generated here and there is a trough here. What does this trough mean? Low pressure. So, this now becomes this small. So, this reduces. Can you see this? So, now the support that you are getting from the stern wave, you are not getting. So, forward resistance more. So, where the wave is generated has an effect on the total resistance of the ship, because it is not only dependent on the wave height as such which determines the pressure, it also depends on the slope of the body at that point.
Then how we control this wave form?
We will see that. Let us not go very forward, but let us understand wave making is a very complicated phenomenon. And at the stern it becomes more complicated because you have got the boundary layer now. Already blunting of pressure is there. So, if I consider a body without any viscosity, I may have got a wave profile which looks like this, but as soon as I bring in viscosity, the wave profile will reduce in size. Then again you see the viscous pressure is coming into effect. Is that understood? Okay. So, this is the wave making phenomenon which is dependent on the shape of the body primarily at the water level and the curvature all along the body, all along the length, and towards the aft end there is a little blunting of the wave making resistance due to presence of boundary layer. So, from this you can understand the wave making part is primarily a contribution of the forebody of the ship. Afterbody does play a part, we will see this, but primarily the forebody. Okay. So, we have this wave making resistance. Now, let us come to the forebody once again. Let us take a very blunt ship like a tanker or a bulk carrier, where the forebody beam is large, block coefficient is very high, 0.85 or even higher than that. You know what is block coefficient, I believe. And then what happens, the water lines close in at the water level, not like this, but something like this. You can see this portion is blunt, a large angle of entrance, half angle of entrance, right. So, the discontinuity is very large. What will be its effect? We can well imagine that it will give a very large wave slope on the surface, because wave will depend on the discontinuity of the body, and the discontinuity is very large here. Therefore, you will get a very large wave, and that wave cannot come along the length of the ship, but it will be pushed out because the body is there. You understand those, we talked about those divergent waves. Those divergent waves will now go very at a large angle,
almost transverse to the ship.
Almost transverse to a ship. So, this wave that is being created will have a large amplitude, high amplitude even at low speed, and it will try to be, it will be pushed to the side. So, the wave slope, the slope of the wave will become high. Do you understand? If I had a wave previously like this, now the wave will become like this. Do you understand? And what is the effect of wave slope? Can you tell me? A gravity wave which has a very large slope, what is its effect?
More resistance to the ship.
It cannot retain itself, it cannot maintain the shape anymore, it will break. What you see in the sea coast, because of the reduction of depth as the wave comes to the coast, the wave height increases and it cannot be maintained and it breaks. Same thing will happen here. A large wave slope will be generated, the waves will start climbing up and it cannot maintain itself, so it will break. As soon as it breaks, like it happens in coast, where does the energy go? In the coastal wave breaking, where does the energy go? It goes in the form of sound and creation of eddies. That is how that wave is totally absorbed by the sand and the water particles, eddies are formed, you see the white mass and the energy goes. So, here similarly, now the wave will not propagate as wave anymore once it breaks. You will see the white mass. You have seen in large ships, you will see the white mass right in front like this. You have seen that? That means the wave has broken. You do not see large waves far beyond. You will see waves in fine smooth ships, but in large bulk carriers and tankers, you will not see those big nice waves that you saw before, but you will see in the front the white fluid, flower like things. So, there is a big difference between these two phenomena. In one case, the waves are carrying away the energy as wave making resistance. In the other case, though the waves were generated due to a potential flow effect, its manifestation is in breaking waves in that this thing, that also takes away energy. Initial formation of this was due to taking away of the energy, but its manifestation is in the form of wave breaking. So, you see, when somebody tells you that in a slow full form ship wave making resistance is almost negligible, it is true because you can't see waves, but there is a large amount of wave breaking resistance. Do you understand? Similarly, in the forward and bottom, there may be eddies and separations exactly for the same reason as we had in the forward aft, because of the sharpness of the curvature. Again, it is a phenomenon of full form ships. In fine form ships like frigates or naval vessels or container ships and passenger ships, this may not be there, but in case of full form ships, this is something which you may expect, that some drag resistance, some formation of eddies and vortices and going away from the bilges of the forward end, forward bilges take away energy. So, there will be that component of resistance also coming up. So, on a surface ship, you will have the wave making resistance. Depending on the forebody shape, you may also have wave breaking resistance. You will have the frictional resistance, you will have the separation drag or eddy drag, and you may also have the viscous pressure drag, which may be substantial, maybe, we do not know. So, if I divide my resistance now into various components, how will I get? There are two phenomena basically, pressure and viscous. I also want to mention to you, please understand that pressure resistance is a normal pressure on the body surface, a normal force. The components in the axial direction give us resistance. The components in the transverse direction cancel each other. Similarly, the viscous resistance is primarily a tangential force, just perpendicular to the pressure. Can you understand that? Pressure, if a body is there, pressure is acting perpendicular, and this is tangential to the body.
So it will be perpendicular to the pressure.
More or less. Understand that there is a boundary layer which makes adjustments. So this perpendicular will be a little bit less than perpendicular. But primarily this is tangential force and this is normal force. Okay. Now, pressure resistance mainly shows itself as wave making. Okay. Then it has another effect, viscous pressure drag. Okay. And what we have seen, it also generates okay, and viscous frictional and separation or eddy making. Is that clear? Now, this is pressure and viscous can be, you can see that these two effects are due to viscosity, viscous pressure drag and wave breaking drag. So, sometimes these two are included in the viscous resistance. Do you understand? Though their origin is in pressure, their manifestation is viscosity. So, viscous resistance consists of all this. So, sometimes the resistance is composed of two cases only, wave making and viscous. Okay. Sometimes we say wave making and viscous, or sometimes we say pressure and viscous, where these components are both reflected in pressure and viscosity. Is that clear? Right. Now, this frictional resistance, we will see this in more detail perhaps in the next class itself, but understand that this is not exactly same as if the body was completely two dimensional in nature. That is, if I had a flat plate. If I had a flat plate which I moved in water, it would have experienced some frictional resistance. If I had a nice smooth streamlined body which did not have ends, it could have been very large in depth and very large in length, which could be considered as a two dimensional body. Again, it would have had two dimensional friction, that is, all the flow would have been horizontal. But when you come to a three dimensional body like a ship, the things change. I like to explain this to you. What we have in a ship is we have a water line, ends come to an end in some shape, and what happens in the sectional plane? There is a bilge which curves in the forward end, this in the middle it's this wide and it curves in, but in forward end this body, this entire body comes in like this. Do you understand? And same happens to the aft body. So, if you look at the body shape, it is highly three dimensional. How does the flow happen around this body? If we start from the free surface, we know that on the free surface there is a wave profile, okay? And wave profile, you have a crest in the front, a trough in the middle and a crest in the aft. Normally this will be the case around the ship. Far away you will have the divergent and transverse waves. If I trace a particle just below the free surface, what will I see? How will the particle go? Will it go parallel to the wave or it will go some other manner? It will in fact go in some other manner. It will normally go very fast downwards, expanding as it goes. If I trace two particles in the central line, one going port, one going starboard, it will not go horizontally like this, nor will it go following the wave profile like this, but it will dip down sharply depending on the curvature of the body. It will dip down sharply, and as it dips down, suddenly near the bilges it finds that it has to go like this, because the body has closed. Do you understand what I am saying? That is, the flow on the free surface went like this, right, but just below the free surface the water will go down like this and then it will go like this. So, you see it has got a transverse component is going out, it has got a vertical component is going down, and at the bottom it has got a change in direction altogether. So, flow is highly complex, and the viscous resistance will depend on this complex flow going around the body, which is no more anywhere near two dimensional flow. Do you understand this? I do not know whether you are understanding or not understanding. In a two dimensional flow, flow will go in two dimensions, that is in one plane, either in the horizontal plane or vertical plane. In case of ships it will be horizontal plane, it will go in this. But when it is going down like this, just imagine the distance travelled is more apart from anything else, plus there may be some eddy making and all those things because of the curvature it is encountering. So, the frictional resistance of a flat plate and a frictional resistance due to a body having the same weighted surface, but a three dimensional shape will be different, right. So, sometimes we say it is a form effect. So, normally this and this three components together we call friction form effect, because it is very difficult to calculate this and this separately, and their effect of form only. So, in conventional components of resistance analysis, we say that total resistance is composed of wave making resistance and viscous resistance, which is two dimensional frictional resistance and form effect, form resistance due to form. Normally this is taken as a percentage of this. So, we have frictional resistance estimated in some manner, multiply by a constant. Do you understand? So, this takes into account separation and eddy braking, wave braking if any, and viscous pressure drag, unless we go into more details of how to calculate each component separately. Am I clear? Can we calculate each component separately? Next question is, can we calculate each component separately? We will look at this a little more deeper in our future classes, but so far as the present technical knowledge level goes, it is extremely difficult to calculate all components of resistance theoretically to an accurate level which can be used by engineering practices, powering of ships or something more than this. So, what is normally done till now is model experiments and how to get the resistance extrapolated to the full scale from model experiments. This you will be looking at more thoroughly. Now, so far we have only talked about water resistance, that too water resistance in calm water. Now, what are the other components of resistance that affect powering of a ship? Some of it you can well imagine. Air resistance will be one. There will be resistance to forward motion in air also. Only thing is, it is very small compared to water resistance. Therefore, we do not go scientifically into estimating air resistance. We have some statistical data drawn from various wind tunnel experiments of the ship above water portion, and we can extrapolate statistically to different ships and different superstructure configurations. Okay. What other components of resistance are there? You have the trial resistance, as we mentioned. Trial will be mainly the air resistance component will come in. Then in a ship you may have some appendages. Typically in a merchant vessel we will have the build skills, and you will have a rudder. Propeller we do not consider resistance because of what? Propeller, if it is left free, if it is free to rotate, then its resistance is very low, but if it is locked, its resistance is very high. You do not normally tow a ship with the propeller locked. So, that is not affecting our powering, whereas the rudder, the appendages, bossings if you have, shaft bossings, shaft brackets, sonar domes in naval vessels, bow thruster units in the forward part of the ship, or stern thrusters, these all add to resistance. So, all those appendages have to be added, and the trial resistance at 0 speed condition can be calculated. Now,
bulbous bow we don't take.
Sorry?
It's a normal part of the hull. Bulbous bow.
Bulbous bow is a part of the integral part of the hull. Yeah.
Not like bilge keel.
No, it is not like bilge keel. Bilge keel is a flat surface. Its effect is mainly in frictional resistance. It is a flat plate, unless there is one little problem with bilge keel. If the bilge keel is aligned in the in a streamline that would flow past the ship, then the resistance due to bilge keel only due to two-dimensional friction. But if it is not aligned in a streamline, the bilge keel itself may disturb the flow, creating separation and eddies. Therefore, before drawing of the bilge keel, before finalizing the bilge keel, it is essential to do a what is called a paint flow test on the model. You have to see the direction of water flow on a model, and based on that you have to align your bilge keel. Otherwise, it will see, whenever there is a flow disturbance, it is not only that the drag is more, it is that you will have a humming sound, because the body will vibrate, and that vibration, if it is sufficiently large, it can affect your ship, which is a case in many small vessels. Large vessels you do not realize it, because the vibratory force is very low compared to the whole ship, but in small vessels which are very much appendage oriented forms. They have large number of appendages like bossing and twin rudders and things like that. They have many times this problem with flow, and this shows up in the living conditions inside the ship, working conditions, even machinery operation, etc. So, normally in trial condition it is told that the ship should be able to the trial speed is to be obtained in a wind speed up to Beaufort scale 3. So, how do we take that into account? It is mainly the wind resistance which is augmented due to the large wind speed. We normally up to Beaufort scale 3 the sea is rippling only, and we assume that there will be no added resistance due to waves. Okay, as if calm water with regard to sea condition, but wind resistance increases because Beaufort scale 3 means it will be another 20 knots or so wind speed added to the speed of the ship. See, when a ship is going at 15 knots, the wind is blowing past at the same speed 15 knots. Now, if on top of that there is a Beaufort scale 3, there is another 20 knots wind added to it. So, 15 plus 20, 35 knots. So, that wind resistance part increases. That has to be taken into account in trial condition. In service condition, it is very difficult to estimate what will be the added resistance due to waves, because wave condition itself keeps varying. Sometimes we assume a standard sea state in a particular seaway, say North Atlantic or Pacific or something. We assume a standard sea condition and we can add some value due to such a sea condition, which may be supported by model experiments, but so much of thoroughness is not required. What we can do is, for sea condition we can add a percentage of total resistance, say 10 to 15% depending on the sea, for service allowance. But what is more interesting is, as the ship goes into service, its paint peels off, the ship corrodes and fouling takes place. That gives a large chunk of increase in resistance. That has to be added to resistance if we really want to get a good estimate of surface speed.
Even the ship's surface you see in big ships like cages, means ribs, where the main ribs are there, the plate goes in the flat plate, that will also affect, no?
Normally not. Such fluctuations in the body surface, if it is within the boundary layer, then the boundary layer takes care of it, because we will see this, we are actually talking about turbulent boundary layer which is turbulent. There are two types of boundary layer, laminar and turbulent. So, if you are talking of turbulent boundary layer, then this is automatically taken care of. Small variations or welt marks on the ship, but on the other hand they add to roughness of the ship. So, due to roughness there is an increase in turbulence, that has to be taken into account. So, but in general we do not bother, because you see previously ships were riveted, lap jointed and riveted, that used to add a large portion to resistance. After the welding has come and with a thorough supervision, the weld mark, the discontinuity due to weld mark is not so prominent. So, what we do actually, if we are talking of model experiments and full scale tow rope resistance comparison, model vessel is very smooth, either in wax or in fiberglass or whatever you make, the model surface is very smooth. But in actual ship the surface is rough, it can never be to that smoothness. So, what we do is we add what is called a correlation allowance, that is a small increase in the resistance as we extrapolate it to full scale, to take into account the initial roughness of the ship, which includes weld marks and any discontinuity in the hull surface. One thing must be understood, any discontinuity must necessarily be small. If it is large, it will create separation. That is not taken into account.
Due to
Yeah, yeah, right. So, we will talk about this when we talk about extrapolation from model to ship, which is going to be our main theme in this set of lectures. We will see how we can take into account such discontinuities that happen. Okay. So, next class we will look at I think we will first look at frictional resistance and then look at wave making resistance and then we will see model experiments. Okay. Thank you.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. That ensure a student's mind develops at the right pace. Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITian out of KGP, but not KGP out of an IITian. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shape their mind and body, a collage of events that was a synthesis of competition and cooperation. A collage of interests as diverse as dramatics and ham radio. Yes, life at Kharagpur has always been exciting. And the years cemented lifelong bonds as lives mingled over cups of joy and stretched over stimulating semesters. The halls with their blocks and wings connected by charming catwalks remain ensconced in their own world. A collage of memories. Infrastructurally adequate, architecturally meticulous, and holistically inspiring. Where students, wherever they might be from, invariably come into their own, developing their individual talents, honing their skills to take on challenges with confidence, so they can move ahead in fulfilling their dreams. What makes IIT Kharagpur so unique is its environment. Undiluted by the diversions of metropolitan surroundings, the close-knit campus life enhances the entrepreneurial and innovative spirit of the achievers-to-be. In an environment that is so stimulating, it is only natural that down the years, IIT Kharagpur has consistently produced well-rounded individuals. Many of them are celebrities in their own right. Holistic grooming has had a lot to do with this. So, no matter which walk of life they choose, the IIT KGPite stands tall. And so does the institution that bred him, in majestic splendor. The alumni of this institute command global respect. Their distinguished presence at the helm of global giants is a matter of national pride. For the students of IIT Kharagpur, it is impossible to erase any scratch of memory about their alma mater. In fact, some come back to invest sentiment, pride, and money, to see the institute they call home rise to even greater heights, structurally, functionally, as well as holistically. Their singular aim is to make IIT Kharagpur an institute whichever way you look at it, par excellence. A man's journey into quiet accomplishment and the Hall of Fame starts with the right step. And the training and placement cell of IIT has been the efficient facilitator in this regard for over 30,000 graduates. Having placed more than 95% of its students in a wide range of industries consistently for over 2 decades, it is no wonder that the institute is the most preferred campus for technical recruitment of quality manpower. With infrastructure like industrial power and communication facilities, in addition to its excellent research and consultancy facilities, STEP, or Science and Technology Entrepreneurs Park, aims to assist the budding entrepreneur into a successful adventure capitalist, guiding him right from the concept, institutional financing, production, leading up to the launch and marketing of the product. With its rich pool of talent and excellent infrastructure, it is no surprise that through the last 3 decades, IIT Kharagpur has developed strong liaison with the industry. SRIC, or Sponsored Research and Industrial Consultancy Cell, was formalized as the Special Industry Interaction Cell in 1982. Devoted full-time to handle industrial projects and consultancies and for deploying and propagating intellectual property. Successful sponsored research projects straddle a wide spectrum, ranging from computers, communication and biotechnology to robotics, photonics and food processing. The setting up of a state-of-the-art VLSI CAD laboratory and tie-ups with GE in areas ranging from vehicle structure design to electrical communication and software technologies are excellent examples of IIT Kharagpur's ever-evolving pioneering spirit. Collaborations with a host of national and industrial majors are a testimony of its proven expertise and research repertoire.
आदर्शाय मादर्शाय प्राणदास्मह्वयम् योगकर्मसु कौशलम् योगकर्मसु कौशलम् योगकर्मसु कौशलम्.
Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.